I've already introduced myself to you earlier, so I need not. There was a time when we used to assign homework to our students. Well, you talked us out of that. Now we do the homework, and you get a few extra minutes of sleep in the morning. So anyway, we have enough flex time that even though we are running just a little late, I hope to make up. We're going to talk about dynamo theory, basics. And before I begin my talk, I'd like to tell you that there is an excellent lecture in the archives of the Heliophysics Summer School. If you go back to 2011, Matthias Rempel gave an excellent lecture on this very subject. I have borrowed heavily from his slides. At one point, I saw myself writing many of his equations and decided that I will simply borrow his. And of course, I've added my own material and my own tilt to that. Let me begin with some information on magnetic fields in the universe that you have already heard about yesterday in some form or the other. The Earth has this magnetic field that's been present for 3.5 billion years, much longer than what it would take for the magnetic field to decay if it were left to itself. It would decay because there are dissipation mechanisms. You pass current through a conductor, the conductor has its resistivity. That alone, if you didn't drive a current to the conductor, would gradually decay away due to the presence of dissipation. The Earth has its own. So you do not have to do a lot of plasma physics. You can just, on the basis of that dissipation, estimate, and I'll get to this estimate a little later too, how the magnetic field would decay every 10,000 years. Furthermore, this is not a steady electric field by any means. As you know, the Earth's magnetic field goes through temporal changes. And we know a lot about this. Dana Longkop talked to you about that. The structures below the layer going down to the core, and how the magnetic field has various components that are time variable as well. You know all this now. Moving on to planets, Mercury, Jupiter, and in Jupiter's case, even the moons, Ganymede, Io, well known to have magnetic fields, Saturn, Uranus, Neptune, and they have large-scale fields. I want to, since I introduced the word large scale, I'd like to make a distinction between what I would call large scale and small scale. And this is going to be a recurrent theme of this talk. And you will see that the dynamo mechanism, which we are going to rely heavily on, can do both. It can produce large-scale magnetic fields of the kind that we are just describing, vast dipolar structures. It can also produce small-scale magnetic fields rapidly varying in space and time. Both carry magnetic energy. But if you have small-scale magnetic fields that vary very rapidly in space and time, and if you average it, in general, you will get not that much magnetic flux. There is a difference between energy, which scales like b squared, and flux, which scales linearly with b. So if you average flux, you can often get zero, even though you have very substantial energy in it. When I'm talking about large-scale fields here, I'm talking about fields that not only have energy, but also have flux. Small-scale fields, which are rapidly variable in space and time, could nearly cancel each other, either when you do a time average or you take a certain volume of space over which the magnetic field averages out. Keep this in mind, because the dynamo can end up doing both things. And we today, we think we understand a fair amount about the small-scale dynamo, and not that much yet about the large-scale dynamo, because it still remains an unsolved, and I would say an outstanding unsolved problem in classical physics. But more about that later on. Moving on to the sun, Sun is a very complex object. It has magnetic fields from the smallest observable scales to the size of the sun. The small scales can be very powerful and intense. The large scales are weaker, but undoubtedly there. And when we talk about reversal of the sun's magnetic field, we are looking at reversals of that large scales field over a 22-year cycle. The small scale fields are rapidly fluctuating in space and time, but they do not have such clear cyclical behavior. Ohmic decay time is 10 to the power 9 years. Now this is interesting because if you compare that with the Earth's decay time, this is significantly larger. So you can ask yourself, well, is it just possible that you don't need a dynamo? That the sun can pretty much hold its primordial fields? For many reasons that I'll get into, I'll argue that this is not a very convincing explanation of the sun's magnetic field, particularly because it has a convection zone. And in that convection zone, you have enormous turbulence going on, which effectively reduces this diffusive decay time to a much shorter period of time. So you're back then to the problem that you have for Earth, but more on that later. Other stars, stars with outer convection zone, this is very similar to sun, and stars with outer radiation zone. When you don't have such a convection zone, there the argument that the fields could be primordial or of primary origin is more persuasive. However, we'll be focusing on sun-like stars, which have convection zones, and for the reasons I just said, given the high level of turbulence in the convection zone, even if the magnetic field in the radiation zone were primordial, the arguments for keeping that on the convection zone are not as persuasive. Galaxies, here, this is in fact a striking astrophysical object, and it has the benefit that the magnetic field in these astrophysical objects is directly observable. Faraday rotation, Zeeman effect, whole bunch of effects that are diagnostics have enabled astrophysicists to measure these sorts of magnetic fields directly. Galactic dynamo is an unsolved problem as well, and there are some who still argue that the field could be primordial for a number of reasons, which not only have got to do with the slow rate of diffusive decay, but also because even if we should solve the dynamo problem for the galaxy, as Russell Culsard and others have argued, that there are some serious issues that bring forth due to the strong gravitational pull of galaxies and how matter is distributed, that makes it hard for dynamo models to provide a very persuasive picture of galactic magnetic field origin. He and some other people have argued that the case for primordiality of the galactic magnetic field is not altogether settled. If you are getting a complex picture here of magnetic fields that is intended, I will not want to suggest that there is one great answer that will solve all this problem in one stroke. Nonetheless, it is clear, if you just look at the general body of evidence, that arguing for primordial magnetic fields is just not a convincing explanation. Dynamo theory must play a role. In what shape and form it does so in various astrophysical and space objects, the matter of intense research. Question? Exactly. Thank you. That's exactly what I mean. And even in those cases where we invoke dynamo fields or dynamo effect, it has to start from a seed field. This is a point, for example, that Dana made in his talk yesterday. Remember the homopolar dynamo that he was doing? He was saying that if you didn't have a seed, well, you won't see much amplification. So even where dynamo is effective, you have a primordial seed. And this often comes about due to something called the Biermann effect, which I won't have the time to go into today, but actually is a consequence of the Ohm's law that we'll be looking at, a somewhat more general form than we'll be looking at today. All of these objects begin with some sort of a seed. Now, when I'm arguing for the primordial case, and I'm not, but if you do, then of course you're saying that at the moment of birth of this object, there was a certain magnetic field present that has persisted to this day. Well, if it persists for a few billion years, then you have something to think about, okay? So let me move on from that to now this question then, which was also driving Dana Lunkop's talk yesterday. Why is the universe magnetized? To be honest with you, when I was in graduate school, I found this question sent a chill up my spine, really. It was that exciting. It was just like saying, why did the universe begin a finite time ago? Right? These are very important, nearly existential questions. And we rely so much on the magnetic field of the Earth and the Earth's magnetosphere to shield us from all the things that could have disrupted life in the universe, that to think that this came about in the universe and continues is an absolutely remarkable question. And it's not surprising to me that a question of this magnitude has therefore taken up the energy and effort of so many people. Well, yesterday, I'm building on the foundation of Dana's talk. He did a marvelous job explaining to you the basics of magnetic fields. And he, in fact, I was taking notes. He had 3 fundamental features in his talk that he said we must keep in mind. If you really want to attack these problems generally, you must have an electrically conducting fluid. 2, the fluid must have complex motions. And 3, the motions must be vigorous enough, as measured by the magnetic Reynolds number, Rm, which is velocity times size times resistivity, divided by resistivity. He actually had conductivity multiplied. I wrote it as 1 over resistivity. And as a toy example, he spent a lot of time on the homopolar dynamo. It's really very instructive. But since he did such a good job on this yesterday, I won't spend any time on this. But the basic ingredients that was in the homopolar dynamo, these 3 things will show up in everything I do. But I'm going into things now today in a more mathematically complex manner. But I do not want you to lose the big picture here, that these features will reappear. So don't be fooled by many partial derivatives and many continuum equations. Keep your focus on the big prize, which is that we must have these 3 features present, and I'll tell you how. The references for this lecture is Matthias Rempel, Volume 1, Chapter 3, Paul Charbonneau's Chapter 6 in Volume 3, and Stanley's chapter in Volume 4. I know you've all read it, so it'll make my job much easier. I really mean it. Okay. As evidence that you have read this, I begin, therefore, with suitable forewarning. We are not any longer talking about simple circuitry, but I'm actually giving you, without any dilution, the type of equations people use to study the dynamo problem. These are the well-known magnetohydrodynamic equations. If you take a standard textbook in plasma kinetic theory, you will start with the kinetic equations, which are the underlying fundamental equation. Take moments, and you will get, through textbook exercise, equations such as this. Beautiful these equations are, but they're derived after a lot of approximations. And those approximations are worth keeping in mind. This is the plasma physics version of what fluid dynamicists would call the Navier-Stokes equation. It's pretty much the word of God in fluid dynamics. They more or less live by that equation. Plasma physics is actually more complicated. The MHD equations work quite well for plasma physics or for plasma systems, but they also break down. And the breakdown of MHD equations is just as interesting as where it is valid. But today, we're going to talk mostly about the MHD equations, and I'll make a few comments about what to do in problems where these MHD equations do not work. So this is the continuity equation for mass. This is the momentum equation with pressure force, gravity, which is totally negligible in laboratory context, but is an extremely important term for space and astrophysical objects, especially large ones. This is the Lorentz force term, and you have tau here, which I'll elaborate on in just a moment, the viscous stress tensor. This is the energy equation. E, pressure standing for scalar pressure again. This is thermal conduction. You have now here dissipation terms, as you would in an energy equation. This is due to the viscosity. This is due to the resistivity. And this is the induction equation. And I'll go over these equations again, especially this one, which will be the subject of a lot of attention today. I said there were lots of assumptions. What are the assumptions? Of course, the validity of continuum approximation itself. Enough particles that you can define averages. If you go out to outer space, particularly in the vicinity of the Earth, you can have as few particles as 1 per cubic centimeters. Compared with that, if you go to a fusion laboratory plasma, it can have densities as high as 10 to the power 18 particles per centimeter cube. You can have very, very large variations in density, and the density drops. You begin to worry more and more whether MHD is a very good system or not. It's yet rather remarkable, despite that, how good MHD can be on the large scales. And therefore, it's not a surprise that these equations are the underpinnings for a lot of global studies that we do. Equations work even when the assumptions break down. But you have to be really careful because they don't work everywhere. Particularly places to watch out for are narrow regions where the gradients are extremely strong. There you will need often to replace this continuum description by fully kinetic equations, and those we won't be talking about today. Though the whole problem of what happens for the kinetic dynamo is a really important set of questions in itself. And if you look at the literature, there is very little theory, analytical theory I mean, but there's an enormous body of now growing numerical simulations which are going back to the basic kinetic equations and trying to understand how the dynamo effect actually works in such kinetic systems. By the way, you will stop me anytime you don't understand something, right? Just like she did, and I encourage you to do that. The other assumptions made in writing these systems are non-relativistic motions. The velocity is much smaller than the speed of light, and low frequencies. Typically, the frequencies are much smaller than the cyclotron frequencies for both ions and electrons. And as is true in all continuum approaches, is something that I've emphasized already, one relies somehow on the presence of collisions of the kind that produce eta or produce a kappa, and so on and so forth. If collisions become very infrequent, as I said again, you should revisit these equations. So what are these quantities that I haven't defined yet, in particular tau? And this is the viscous stress tensor tau, which is defined here, nu being the coefficient of viscosity. And this tensor, which has two indices, is really the rate of strain. And you can see it's symmetricized with respect to I and K. So if you exchange I and K, you get the same quantity. This is, in fact, your thermal heat transport. Again, tau IK occurs here. I'm doing this not because I expect you to remember it, but just in the interest of completeness. People are writing codes with these things in. As long as you understand the physical significance of what these terms are, don't worry about the details. For the purpose of this summer school, some of the numerical results that I'll be showing to you from the work of Matthias Rempel or others, or Paul Charbonneau, these are all things that are built into the codes. Ohmic dissipation, this doesn't surprise you, eta times J. J is curl B, eta J square makes a lot of sense. The equation of state, the pressure is related to the quantity E by this expression, where gamma is the ratio of the specific heats. Here, eta, nu, and kappa are the viscosity, the magnetic diffusivity, and thermal conductivity. Mu 0 is the permeability of vacuum, written in MKS units. Any questions so far? So if you look at these system of equations, don't have to worry about the details. You have a complete set of equations to solve if you provide appropriate boundary conditions. Now, as promised, I will focus on the induction equation. The later in my talk, I'll tell you why a preoccupation with the induction equation, I would say, has taught and at the same time set us back in dynamo theory in significant ways. Somehow we had this complicated set of MHD equations, right? We said, we want to understand how magnetic fields are generated, and the first step is, think you have a weak magnetic field, and a prescribed velocity field. How will the magnetic field grow given a certain velocity field? So now we have thrown away everything out of the problem, all the momentum, the continuity, and everything, focusing on one of those equations. And I just want to take that equation apart a little bit. The original equation was E plus V cross B equals this term, which is eta, or 1 over mu 0 sigma times J. Well, combined with Maxwell's equations, curl E equals minus del B del T, you can eliminate E, right? You can take the curl of this equation, replace curl by del B del T. That's how you got the induction equation. Are you guys with me? Okay. What strikes you about this equation when you stare at it? In terms of B, what's this equation in terms of B? Am I asking my question precisely? Is it a linear equation or a nonlinear equation? Linear in B. So if you actually prescribe the velocity field, this is a very tempting equation for both physicists and mathematicians, especially mathematicians. So just imagine all the beautiful family of solutions for velocity that you can dream of. You don't have to worry about the full set of MHD equations. Just keep prescribing all the velocity fields you want, and you'll be able to solve this equation because mathematicians know cold how to solve linear equations in B. This spawned an enormous amount of literature in the field. And some of the nonlinear dynamicists in the 1970s and 80s got involved. We got a happy marriage of MHD induction equation and a lot of nonlinear dynamics, chaotic dynamics stuff. And out of that came out a lot of literature. I'll go over some of that in brief today. But don't forget that we selected out of the entire family of MHD equations, and this particular property of linearity in B, you could not say for any of the other equations where B occurs. Let's go back. Look at this equation. I'm teaching you to be skeptical of anything that theorists or mathematicians throw at you. But look at this equation. This is not linear in B, right? J cross B has curl B cross B. And with this nonlinearity, we clearly are having a particular feature of the equations that's going to come back and haunt us if the magnetic field begins with B and goes to sufficient magnitude. People didn't worry about it for the longest time. They thought that the dynamo problem was solved because they could solve this linear equation. Now, nonlinearity is hard, so it took them time to go out and write big computer code which can actually solve it, and then the problems of kinematic dynamo theory or linear dynamo theory became evident. But I want you to remember this. I mean, there was another approach we could have taken. We could have said, you want to study linear problems? Okay, great. Take this entire system of equations, linearize them, all of them, and solve them together. We didn't do that. We actually chose to focus on one induction equation. And I would say that would have been the more sensible thing to do, but that's hindsight. Okay, let's move on now to the introduction of some dimensionless parameters. All your spatial scales, take your typical length scale, system size if you like, and divide it by L. Take a typical velocity, constant, and scale all your V's that way, and time by L over U. Once you do that, you can cast the equations in dimensionless form, and that eta term now becomes this term. Now, of course, you could non-dimensionalize B as well by defining by dividing with respect to some characteristic value, but that's not so important because B is sitting in all these equations, in all these terms, pardon me, and so whether you non-dimensionalize B or not is do that just to be consistent, but it's not as important. What is important is that you got a magnetic Reynolds number, U times L over eta. This was exactly the number that Dana introduced yesterday. And now if we look at this equation, we have two regimes. One where Rm is really small. We call this the diffusion-dominated regime, because if Rm is so small, this term becomes a rather large term, and we can presumably drop this particular term. Well, we have to be very careful about this, because we are assuming, of course, that the curl of B is simply B over L, L being the large scale. That doesn't always have to be the case. Anyway, so if you take this equation, you can solve it. This is like the heat equation or anything. This is what I was referring to before. If you have a magnetic field in a solid conductor, no velocity, the magnetic field will decay. You can solve this problem, right? Here, del is, by the way, the Laplacian operator, del square. You know how we are getting that, right? Because you have curl of B, and the divergence of B is 0. Just expand that vector identity, and that's what you get. Are you guys all with me? No questions, right? Okay. So the characteristic diffusion timescale is then L square over eta. This is good, which allows us to quantify how the magnetic field would decay. Now, go to the other limit, but Rm is much greater than 1. Then, of course, you can drop that term. It had 1 over Rm in it. And again, I repeat for caution that 1 over Rm term multiplying this term, be careful. I'm going to neglect it, like I said. But when can I not neglect it? Can you think of a situation where I cannot neglect that term, even though 1 over Rm is small? All spatial scales, right? What if the gradient is very, very large? And these are special places in plasma permeated media. If you have gradients that built up very, very sharply in small regions, even though 1 over Rm is a small number, if 1 over gradient, just like Lee said, if this is a small spatial length, there's a small number here divided by a small number there, this term could potentially become of the same magnitude as other terms. It's called boundary layer theory. For many of you who know this term, this is typically what happens if you have a fluid near the wall, right? You can neglect viscosity everywhere in the fluid except when you get near the wall, because you have very, very rapid changes in the velocity field, which is forced to go to 0 near the wall. So I'm going to neglect it, but remember I was telling you that these sorts of neglecting things you have to be careful about, and keeping that term is extremely important in those regions where the gradients are very sharp or at the scale lengths are small. Just as Lee said, I'm going in the opposite direction, pardon me. So now, allowing for the fact that I'm not looking at those small scales, I can throw away that term. So this now looks like the ideal equation. So if I write this out using vector identities, I get V dot grad B plus B dot grad V minus B del dot V. Let's talk about the physical significance of each term. This term is simply the advection of the magnetic field. If you move it to the left-hand side, then del B del T plus V dot grad, you can take del T plus V dot grad and make it into a d dt. That's like the Lagrangian change of magnetic field as a function of time. This term has shear, gradient V. You prescribe a velocity field with shear in it, the magnetic field can stretch with the shear. A very, very important part of any dynamo mechanism, that it stretches magnetic fields. And then on the right-hand side, this is amplification through compression. This can be important, but is not essential to the dynamo mechanism. You could conceivably think of working with an incompressible plasma where del dot V would be 0, but you would still have shearing. and you will have the basics for dynamo theory. Though the amount that you gain by compression can be important in certain contexts. So to return to a motivation for the dynamo again, if you didn't have any V, you know what happens. The magnetic field decays on a time scale of tau d, L square over eta. With me, right? Questions? No? Okay. In Earth and other planets, the evidence for magnetic field on Earth, as I said, is 3.5 times 10 to the -9 years. And this tau d is what I was referring to when I said 10 to the power 4 years. Clearly, there is a reason for doing this. And in fact, the first guy who clearly pointed the way on this was Sir Larmor, who pointed out that something must give here. You cannot understand the Earth's magnetic field. And so he went out to say that you have actually a self-excited dynamo. If you take the quotation from his paper many, many years ago, he was the first person who actually talked about the so-called self-excited dynamo. Now, permanent rock magnetism, not possible, since the temperatures in the Earth's core, as Dana pointed out to you, is well above the Curie temperature. And over that, objects lose mechanisms, lose magnetisms. And the field is highly variable. Field must be maintained by active processes. The sun and other stars, the evidence for solar magnetic field for 300,000 years. Most solar-like stars show magnetic activity independent of age. Indirect evidence for stellar magnetic fields over lifetime of stars. But for these, as I point out, if you forget turbulent diffusion, that diffusion time scale is 10 to the power 9 years. So it's a lot longer than it is for the Earth. But that diffusion time scale can be reduced significantly due to diffusion. And this is the point I'm making again. The primordial field could have survived in radiative interior of sun, but convection zone has much shorter diffusion time scale. More of the order people believe that as short as 10 years. And this is ascribed to turbulent diffusivity. Now, even the subject of turbulent diffusivity, of course, is not a completely straightforward issue. It stands to reason. You must have seen this with coffee and cream, right? Early morning, if you're sufficiently awake, take a cup of black coffee and drop just one droplet of cream. If you wait long enough, that drop, bombarded by all the molecules in the gas, would eventually spread out. And if you wait long enough, your coffee will be cold, but you will eventually have coffee in which that drop will eventually fill, purely by Brownian motion, the whole cup. The coffee can mix with cream without turbulence. But if you take a spoon and you stir it, that's instantaneous. You churned up the system through convection and turbulence, and the rapidity with which that cream diffuses over a much shorter time scale than you do in the other case. That's what I mean by turbulent diffusivity. It's proven that in turbulent systems, I'll take your question, you can do that. But I don't want to suggest by this, based on this very, very simple empirical fact, that I can tell you what the turbulent diffusivity of a system is. Even that particular problem, trying to figure out how rapidly cream should diffuse into black coffee, is fundamentally an unsolved problem, though people have estimates or simulations. Question? True indeed. And there all the terms are of comparable order. He was saying that if Rm is of the order 1, not very large or very small, what would you do? And I would say that I'm not going to be able to discuss that in any one of these limits because all terms are comparable. And it turns out to be a problem of some importance as well. So getting back to some real estimates, for the Earth core, this is eta, and plasma conductivity is 1, turbulent conductivity is a lot larger, and liquid sodium. You know, I want to emphasize to you that something that I'm not covering in this talk has been an object of quite a bit of attention by a few groups, but they have done important work. People have done, using laboratory facilities, liquid sodium experiments, Karlsruhe in Germany. There is another one going on in Germany again, a very big experiment, the largest of its kind. Then in addition, there are laboratory experiments like the plasma dynamo experiments that Carey Forrest is doing at the University of Wisconsin-Madison. Those are actually places where one learns a lot about dynamos. And the only problem is that, liquid sodium is a great place to do an experiment, but the astrophysical objects are rarely made up of liquid sodium. So you have this issue of liquid sodium is very well described by the MHD equations, and that's why that's a valuable thing to do. But there are lots of systems that are not described by the MHD equations, and using liquid sodium results to apply to them would be a bit of a stretch. And people who do these experiments are, of course, well aware of it. So these are the typical scales: Earth, Sun, the lab experiments. These are typical velocities. These are typically magnetic Reynolds numbers that people have. Sun, without turbulent diffusion, enormous range of tau d, but with 100, it's 3 years. Pick your pick. We still have a dynamo problem. What then is the mathematical definition of a dynamo? And this now brings me back to this issue that we talked about, the large-scale dynamo and the small-scale dynamo. And we've got to make this more precise. Are you guys with me? Okay. Consider a bounded volume S with a surface delta S, and B is maintained by currents within S, and B decays as 1 over r cubed over long distances. Then, in the original way in which the dynamo problem was defined, the large and small scale, we picked out of the entire family of MHD equations this one equation we all love, the induction equation, which is a linear equation in B. And we stipulated that outside of that volume S, we have vacuum field. Across S, n dot B is 0. Del dot B equal to 0. V equals 0 outside of S, n dot V is 0 on delta S. And we define kinetic energy as simply the kinetic energy half rho V square integrated over S. This, we argued, would be less than some overall bound. It's not infinite, bounded from above by E max. Then V is a dynamo if an initial condition B equals B0 exists, so that the magnetic energy is greater than some lower bound E min. Are you with me? If you look at this mathematical way to define it, you can see that it actually encompasses a number of the physical possibilities that we just talked about. It can be variable. The only thing is that you prescribe it. It's not determined self-consistently by solving the momentum equation or anything like that. Imagine you have complete control over it. Okay? So that's definition of the dynamo in general. That does not make the distinction between small and large-scale dynamo. This is what we do now. Yeah. There is no upper bound. You're right, because thank you for that question, because you can sort of feel that if you have a linear equation for B and you prescribe V, a possibility that can grow exponentially, right? So strictly speaking, you can take the exponential solution and go to the t going to infinity limit, and the energy would go to infinity. In real fact, will that happen? No. What will change? What will change is non-linearities in the problem are going to prevent you, but not in a way that is given by that linear equation, is what I was driving at. But within the limits of the linear induction equation, there is no non-linearity that can quench it. So things start exponentially in the beginning, will continue to grow exponentially for all time. Okay? Which is why we did not put an upper bound. But there we are going beyond the realm of validity of the equations. So now, going back to the distinction between large and small, decompose the magnetic field into a large-scale part, averaged. This could be averaged over some kind of a spatial average. Like, if there are clear separation between small scales and large scales, you can say, I'm going to average out over a spatial scale larger than the fluctuation scale, but smaller than the system size. This artificial separation may not be always good, Because if you look at the sun's magnetic field, it's there on all scales, from the small to the large. So where do you draw a line and you say, that's my large scale field and that's my small scale field? People do it, but you'll be right to question it. On the other hand, in some other cases, this separation is very clear. For a laboratory magnetic field experiment, take a fusion plasma, for example, which has a very large externally imposed magnetic field. The fluctuations are always a small fraction. Almost always, a very small fraction of the external field. Delta B over B can be of the order of 1 over 10,000. Well, it's clear separation in scales, then the averaging procedure is valid. Now, if you write out it into average B plus B prime, this average could also mean time average. Like if you have many realizations of the system, start out with different initial conditions, this is usually quite better done mathematically than it is done in real life, because you have to produce identical replicas of the system. That's not always possible. So you have average B plus B prime. This is average B squared plus B prime squared. What happened to the cross terms, B and B prime? Why? Okay, good. Why is it 0? Thank you. So when you write out the magnetic field, and if you're doing the volume average, and you say B prime is varying very rapidly over the volume, the cross term vanish. So you get definite contributions from the large scale field and definite contributions from the small scale field. This is what I was referring to earlier. Remember I said that you can always get energy, because no matter what the sign of B prime might be, when you square it and you average it, it's positive. But if you took B dot dA and averaged it, that's a single power of B. The positive and negative signs can cancel out. So you can distinguish small and large scale by saying all carry energy. The large scale produces flux. The small scale does not. Small scale dynamo is when the small scale overwhelms the large scale's energy. That's a small scale dominated case. In the large scale dynamo, when the reverse happens. In almost all turbulent velocity fields are small scale dynamos for sufficiently large Rm. Large scale dynamos require additional large scale symmetries, and we're going to get to that in the second half of this lecture. Are you guys with me? So what I'm saying is, take your random velocity field, integrate that equation, either numerically or analytically. You will find it's very easy to get small scale excitations. And the literature is full of these things, people solving. This is the nice thing, is when you get mathematicians involved, you get all kinds of exact solutions, but if you allow them to dominate the game, you're in trouble, as we will see. Now, as applied to the sun, what's going on? Well, this is a full disk magnetogram, SDO HMI. You've seen such pictures yesterday. Very intense concentrations of magnetic fields happening below the surface, pushing their heads above. The sun is a complex story. It has intense, strong, small-scale magnetic fields and a weaker, large-scale magnetic field, which shows this wonderful cycle that we have talked about, right? And this is the movie, the classic Hathaway movie that you have seen. And I think, Dana, did you show it yesterday? You didn't? Okay. So, no, not at all. I'm glad I don't feel so redundant. Hathaway did this beautiful movie over 25 years, and you see that the magnetic fields have all vanished and they come back. And if you really plot this out, they really make wonderful butterfly diagrams. It's one of the most beautiful things you will see. The sun's magnetic field dynamically and in space, evolving in space and time. And this is the most interesting story that we are still working hard on figuring out. Well, what happened was, in the case of, I was telling you, a whole family of work that developed what we call fast and slow dynamo models, which take that induction equation and just prescribe velocity fields and figure out how magnetic fields behave. And out of that, in conjunction with all the developments that were going on in nonlinear dynamics, people did chaotic flows. You know, cream and coffee, chaotic flow, an example of that. So typically there are two ingredients of these models. Here is a magnetic field. You can proceed in one of two ways. You can take this and you can twist it. Rubber band, twist it. You've all done this, right? You build tension in the magnetic field. You also build this intensity as you extend it. Then you fold it over. There's a little pinch there. If you don't do anything at the pinch and continue the twisting, you will find that the pinching is going to start resisting you. That's where you need to have something called reconnection. And I'm going to tell you just 2 slides what reconnection is about. Most of you know what that is. But what I wanted to say was that if you just continue just twisting and folding, this is going to be a recipe for disaster in the long run, because the magnetic field is going to continue to get twisted and very entangled, and there's going to be no relief. Just like a rubber band, you're trying to twist many, many, many times, and you'll find that it resists after a while. So something has to happen. This is to pinch off, and you get 2 additional patches. Then you can do the same game over and over again. So this is stretch, twist, reconnect, stretch, twist, fold, reconnect. That's one pathway. Another is that you could just do simple reconnection by pinching them, in which case you get this. In this case, the reconnection speed is often very, very slow, and you can get these sorts of reconfigurations in both ways. But remember what you want to do? What you want to do is to get to a dynamo effect, which would be independent of dissipation. Because the dissipation coefficient, eta, is very small in many cases of interest. If something gets all tied down with eta, you're going to get into trouble. So what happens is these features are important in all of these scenarios. You have amplification through field line stretching, twist fold required to repack fields into the original volume, and magnetic diffusivity allows for change of topology. But I must tell you what this change of topology is about, and this actually, brings me to what reconnection is. Most of you know this, but just for completeness, I have 2 slides on it. So I'm taking a little digression here to just tell you about that pinching process. What is that pinching process? Well, that is magnetic reconnection. Now, what is magnetic reconnection? If you had no dissipation in the problem, E plus V cross B equals 0, then you had Alfvén's theorem. This is one of the things that Alfvén got the Nobel Prize for. And actually, it turns out that he believed in his theorem so very much, actually a great and powerful theorem, that he didn't believe in reconnection for the longest time. And so that great man got in seriously in the way of our developing an understanding of reconnection for a very, very long time because of his own theorem. And his theorem said, not a whole lot of room you have. If you have this equation, if you take a circuit, imagine this is made of a plasma fluid elements and permeated by magnetic fields. You allow things to evolve, it deforms slightly after a very short period of time. And if you follow through longer, this will become more and more complicated. But the flux enclosed in this area will always be constant. The other version of Alfvén's theorem is the following. It's an alternate statement that suppose if you took a field line and stuck plasma elements to it, like beads on a wire, Alfvén's theorem tells you that as that field line evolves, the plasma elements you put on it at time t equal to 0 will remain on it for all times. So there is no slippage of the plasma elements with respect to the magnetic field. This is what happens if you don't have any dissipation. If you have any dissipation, then you break all these strong topological constraints in the magnetic field. If on the right-hand side, instead of 0, you have an R, and R has the property that the curl of R is non-zero. Remember, eta j is such a term. Curl of eta j is non-zero because j is curl of B. Eta is non-zero, that's non-zero. But gradient pressure, if you take the curl of that, it vanishes. The gradient pressure has a very interesting and subtle effect on the reconnection process, but it cannot break field lines. This is good to keep in mind. But moving on, curl of R not equal to 0, then you can have the following phenomenon. Field lines pointing in opposite directions, they come together, they break and reconnect, and by this process can release enormous amounts of energy. So what I'm relying on is a process of reconnection sufficiently fast at those pinch points that this can go on. sufficiently rapidly. So what happened out of this study was that you got two classes of dynamos, and after this slide, we'll take a little break. The influence of magnetic diffusivity on growth rate. You have fast dynamos, where the growth rate of the magnetic field, people found velocity fields that makes the B go like B0 e to the power gamma t. What is gamma? In the fast dynamo case, gamma is independent of Rm. Those conform to the stretch, twist, fold mechanisms, and trying to obtain those flows. Remember, that's the first step in the problem. You're not even talking about the full MHD equations. But can you come up with a flow which will give you growth of the magnetic field from a weak seed? That's fast because the gamma is independent of Rm. In the slow dynamo case, the glow is limited by resistivity. As I was saying, most astrophysical objects have to rely on fast dynamos. And these assume somehow that the reconnection can be fast enough that they won't hold you up while you're stretching, twisting, folding, and breaking. If that break does not occur fast enough, the dynamo process gets throttled. Therefore, solving the problem of fast reconnection becomes an important step in solving the dynamo problem. And people have been rather creative about that, but I have no time to go into that today at all. Let's take a break, and we will continue from there on, because I just noticed it's like 45 minutes already, right? About that. Thank you. Make it a short break. I already gave up 10 minutes earlier, so try to get back in 5. Thank you. But then the question is, how we can make the Rm dependence? Term will come in. But even if the term comes in, the question is, in the limit of Rm going to 0, how does it depend on Rm? And so people have been able to reduce the Rm dependence to either logarithmic or the log of log, and so on and so forth. Big dependency, exactly. pace just a little. Go back and try to make connection with something. Lectures by Mark Mead, who's an expert. So I want to talk about one of the beautiful things about the sun, helioseismology. Learned a lot thanks to observations. Remarkable things about the solar convection zone. That zone in which very narrow region called the tachocline, beyond which dominantly radial, arc gradient. Some of you. What I want to do is to talk about the magnetic field. As is to actually highlight the problem Dynamo in the context of so the magnetic spherical polar mode. I is into the toroidal field described by the scalar potential. So the field is del phi is 0 for this. Velocity field components r and theta in the plane. Another in the phi direction, which is the rotation is the most dominant shear flow in this. Also there in the surface flow. This is the flow pattern. And if you say I go back to the induction equation and write out time-dependent equations, don't be component, write everything out. Del is the del square operator. One component is described by the scalar quantity A. Solve these equations, you can solve them. Rotation is this term. Right and there, you wouldn't have a source for the toroidal field. The toroidal field would just decay. Just convection of the toroidal field. On the right hand side, you have dissipation. Stop your in the manner in which Dana talked about yesterday. And this is actually made more precise by this statement. Currents limited to a finite volume in space cannot be maintained by a velocity field with finite amplitude. Ohm's law and look at what is called an O-type neutral line with the magnetic field close to the other. On this O-type neutral line with the magnetic field, the field line close on itself, have U0 JT as curl of VP. This value, but it cannot. What I just said to you a moment ago, just a little bit more rigorous. So where do we go from here? We need a flow. We need something in the now that we are into elsewhere for a very long time. So how does mean field dynamo go about tackling this problem? You set the induction equation again. Now you go mean B. Average that equation. Average cross B average. Average. What you get? Why isn't there a term which is simply linear? Right. Actually, an exact equation. Subtract this equation from the total equation, an equation for the fluctuation. That's this equation. Solve for the fluctuation. Right hand side minus V prime plus V prime, but there's another term. We want to solve the second river. Now, what's our game plan? Our game plan is that we want to figure out how the average B field is evolved. Solve this equation for B prime. Solve the same. Solve the equation for the B prime. This is linearity B prime. Equation then. Time evolution of V prime plus V prime. Like that equation, you will find that it depends on a triple. Or typically the problem of kinetic dynamo theory did was that it brought that up. By Matthias Rempel in the chapter, I'm going to go through some steps of it. After dropping that term, the problem becomes a lot simpler. Are you guys with me? We made an important approximation. We dropped that. Solve that problem. And the question is, what is E, I in that, which is V prime average? That's what it's called in code. Or now with the fluctuations. Right, such a system, can show that that turbulent EMF has two terms. Parallel to B. This term is extremely turbulent EMF parallel to the background magnetic field. One can write this in fancier form. Belabor this point, as I said, is worked out in the textbook. Find that E can be written as EI, alpha IK BK. Are all tensor forms for the turbulent EMF. And if you write this in coordinate independent form, alpha, gamma term, beta. Beta is just like your resistivity, if you will, if it were a scalar. In general, this beta would actually also be a tensor. Turbulence can produce both alpha and beta, and this is something a rather general variety. And near the end of my talk, I'll point out to you what this gives us a possibility for doing, some novel methods are possibly done. A particularly simple form for dynamo theory that's very popular, so it's worthwhile to get down to it. And you will not get dynamo effect in the way in which we want it in order to act. Turbulence must have a certain property that will break its mirror symmetry. If it's mirror symmetric, then this alpha is going to be 0. And back to the old problem where all that the turbulence has done. Turbulence plus something more, non-mirror symmetric, and those conditions one can show that this alpha tensor, alpha, beta, becomes also a scalar. This is all diagonal terms now. Terms that I'm going to highlight are alpha B term. Alpha can be shown. Radler, following a wonderful suggestion from Parker regarding the kind of alpha effect, which is product of V prime dot curl cross V prime. This is called the vorticity of the fluid, called the kinetic helicity. And eta T is in fact the turbulent cloud due to turbulence. We don't have kinetic helicity in the system based on simple not the alpha effect. Was in the identity actually cases of fast dynamo. I want to simply make the point that the presence of kinetic helicity, pardon me, is what gives alpha its primary character, but it's essentially this is in terms of direction. Shows preference for a particular direction. And in certain cases, also prefer direction that they approximate. Analogous to the alpha effect leading to alpha light and dynamo effect that I'm sure Mark will discuss in his talk. I want to return to what the alpha effect will actually do. Equations that you and I just looked at a few minutes ago. The induction equation. There in the solar convection. Where we had no alpha effect. Furthermore, because N is what we call Dynamo operative level of kinematic theory. If turbulence would not be mirror symmetric, then we have a way to actually anchor the magnetic field in the convection zone. And this is now a simulation result that Matthias Rempel was kind enough to give me. And what I want to show you is what happens if you take those induction equations and you just integrate them on the computer. And you will see that the magnetic field goes through a cycle from where it was, and look at the years, and by the time you get to the 22-year cycle where you started has returned. See that again. You started from that pattern, and imagine you gave an alpha, gave an omega, and you integrate those equations. No, I'm sorry. I wanted to start the movie again. That's where you started, and that's where you approximately end. So this interplay of poloidal and toroidal field given an alpha effect can take you back actually started. However, this all assumes that you have an omega, an alpha. Parker once said, all the magnetic fields in the forms for alpha and beta. It presumes the whole exercise took a life of its own. Body of that which is full. What it did not address was a very, very important issue. Started out this lecture with, and we commented on it, is that as the magnetic field grows in strength, non-linearity is the problem will become tremendously important. What will they do? In the momentum equation, look, we had a J cross V term. Presence of the fluctuations, now we are back to the momentum equation. Or the induction equation for the moment. We're now looking at the J cross V Lorentz force. That J cross. in the induction equation has to stop somewhere along, and the question is when it stops. This became a very controversial problem. There's one that was a thing that pointed out many, many years ago was that if you take into account the effect of that reaction, then the alpha theory, remember that was minus 1/3 tau c omega dot d prime, it modified by j prime dot d prime. That is coming about at later time. If you think that plasma physics contains a whole lot of wave waves, are roughly like 3 proportional to third of both sides of the equation. It's clear that the back reaction path of alpha waves. Well, a lot of numerical work got done. The quenching was a serious problem. There's been a lot of controversy in this, but let me summarize the situation. There are real challenges to mean field kinematic dynamics. Smaller scales grow most rapidly. Also, the Anderson made this point. If you have a mean field, so that with a lot of fluctuations. Then, due to constraints of magnetic helicity conservation, small-scale fields act back to decrease the large-scale field growth drastically. Problem of catastrophic quenching. Challenge could be addressed by bringing in helicity from the outside. And this is what I mean by controversy. What happened was that the Chicago school followed a lot of simulation. But it was that reaction. So this created a controversy, and Eric Blackman, George Field, and others got into this way, and they said the considerations of Catania and others are incomplete. Yes, helicity internally does what they say, but what they've forgotten is how helicity can be transported from the outside to the inside. And they found ways of getting around this quenching issue, and some of those arguments are quite convincing. At even moderate RM, the fast-growing small-scale dynamo implies that velocity fluctuation should always be accompanied by magnetic field fluctuations. This is another wrinkle. Think about the kinematic induction equation. What do we say? We say we control the velocity, and that velocity then controls how the magnetic field grows. But you also have growth of magnetic field fluctuations themselves in the problem, which should be treated on an equal basis as the velocity field fluctuations too. And if you would indulge me for just a few more minutes, because I indulged you at the beginning of the talk, I want to go on just a couple of slides to tell you where the dynamo field is evolving right now. And there are lessons to be learned here from astrophysics that might have some bearing on the problem of the solar dynamo, which is one of our principal objects of interest in this summer school. What happens in astrophysics is, you can ask me this question: can you give me one example where people have ample evidence to believe that they have a large-scale dynamo? Well, observationally, people have astrophysical observations, inferred. Astrophysicists don't have in situ measurements. Everything they know is by counting photons. So that's very delimiting, which is why you have so many astrophysical theories for a single observation, and they all get away with it because we don't know a whole lot more. But this is actually one of the classic problems in astrophysical theory, which is that suppose you have an object in the vicinity of a black hole. It has an accretion disk around it. How does the accretion disk form? An enormous pull of gravity. It puts material out from a star and has it flowing in disk. And the transport of angular momentum on this disk, as well as the presence of a large-scale magnetic field, are things for which there is ample observational evidence. Not detailed measurements, but indirect evidence there is. People try to simulate this accretion disk in using MHD equations. Now, with the limitations of all simulations, and this has been done by many people, this much you can buy into, that people have done full MHD simulations of accretion disk flows and have come to the conclusion that globally you can produce large-scale magnetic fields. Go and do a search on Google. You'll find tons of simulations and papers that make this point. So we have a numerical result. Question is, do we understand it? How do we come to understand these large-scale flows? Because look at where kinematic dynamo theory left us. Okay, it predicted a growth, but then it didn't take into account non-linearity. When you take into non-linearity, then you get quenching. Well, if you have quenching, is the alpha effect very effective or not? Well, an undecided question. You go out and do a simulation with the full MHD equations, you do get large-scale amplification. So there must be some variant of an effect that is allowing the magnetic field to grow to large scales in the first place. What is that? What is this result that the codes are actually finding? Well, to do this problem in the global domain is really hard. What happens is that in these systems, there is actually an instability that I don't have the time to go into, which is called the magnetorotational instability. It's basically an instability that is made possible by the existence of a background magnetic field, but it primarily owes its origin to the existence of shear flow. Take it from me that the linear instability properties are very well understood of this magnetorotational instability. There are even lab experiments which are try to verify this effect. But numerically, to follow an accretion disk in its full glory is very hard. So what people do is to take a small block of it, blow up. They call it a sheared box. And they try to study in that sheared box what kind of magnetic field do you actually get. And here actually I am going to report to you a result of my former student, Jonathan Squire, who actually just was given the Marshall Rosenbluth Dissertation Prize for his work on the dynamo for accretion disks. And Jonathan found something exceedingly interesting, and I just want to leave you with his results, which are the subject of about 8 papers now, all written with me, but he deserves the primary credit for having done all the heavy lifting. I was there as a sparring partner. And basically what he did was that he studied in the shearing box, and he found, in fact, that you get large-scale dynamo like others have. But he did more. What he did was to point out what the mechanism is for producing this dynamo mechanism. And he actually went to a case where there was no kinetic helicity at all. So there was no alpha effect. So you will say, but you just told me that there is no dynamo without the alpha effect. But remember, the original equation was E equals alpha dot B plus beta dot J, where alpha was a tensor and beta was a tensor. And then we simplified it to a scalar alpha and a scalar beta. What Jonathan did was to argue that if you take no kinetic helicity, but if beta is a tensor and it has off-diagonal elements, then negative beta can in fact drive a dynamo in the problem. And he argues a novel mechanism, therefore, which he calls the magnetic shear current effect, which leads to amplification of the magnetic field due to the presence of off-diagonal elements. And he does extensive analytical and numerical study to make that point. And what is happening in this problem, and he also does numerical results. So let me end with this last slide. what he points out is pretty much to put dynamo theory on its head. Remember what we were talking about regarding what is going on with small and large scale? We said that the small scale dynamo was really bad for large scale growth. Remember? The back reaction problem we started talking about. What did Coulthard and Anderson say? They said, you start doing this magnetic field problem, you'll have enormous growth of small scale fluctuations, which is going to overpower any mean field growth that you get. And then the Chicago School and others came around and said, that fluctuation in turn is going to quench your alpha effect early, and you're not going to get much mean field amplification, which Blackman and Field tried to get around by talking about helicity transport and all of that. What Jonathan Squire is saying is, throw all of that out. Is really the small-scale dynamo all that bad? And so here he's questioning that. First, you get fast growth of small-scale dynamo. He doesn't question that at all. And then those magnetic fields rise to the level of fluctuation, where now you have in the system the small-scale velocity fields by turbulence, as well as the small-scale magnetic field fluctuations produced by the magnetic field fluctuations, now driving on a much longer time scale a large-scale dynamo. So the magnetic field fluctuations, which were deleterious on the short time scale, eventually end up driving mean field growth in the system. And he makes this problem precise by using perturbation theory and shows he can do perturbation theory only in the limit of small Rm, where he demonstrates analytically that this effect actually occurs. And for large Rm, he actually does numerical simulations. So this opens up, in my view, a new possibility for dynamo theory. Now, as to whether this is going on in the solar convection zone or not, we don't really know. But there's a very nice paper by Hotta, Rempel, and others, which is that in the Sun, their paper, which appeared in Science, is a beautiful piece of simulations. And the point that they make is that if you really want to understand the Sun's large-scale magnetic field, you must, in the numerical experiment, resolve the small as well as large. They did their work independently, and as did Jonathan Squire, and the papers came out at about the same time. And if Squire's hypothesis is in fact correct, then a possible explanation for the Hotta results could be that what you really have is rapid growth of the small scale that in turn later on bootstraps to help the mean field grow, as seen in the Hotta et al. Simulation. Let me stop at that to just give you a sense of how rapidly this evolving field is, and there is still room for a lot of you to contribute to the problem. Question? Beta tensor effect, not the scalar. Sure. There are other possibilities. Yes, I didn't dwell much on the delta term. And if you look at the general term, there is room there to do amplification. And it's good to keep that in mind. In this particular case, if we didn't allow for tensorial beta, we wouldn't understand these results either. We think now that evoking that. Now, if you put in helicity back in the problem, of course, that would complicate this. You might get additional growth. You might have the two effects not supporting each other. All that work remains to be done. And your delta effect, if you would say, possibility, I haven't thought about that. That's any other questions, comments? Yeah. Let's see. Should we attribute that to the compass deflections? Oh, you're asking me how, not when it was seen, but when it existed? Well, right after the Big Bang and after the first couple of minutes, I think there are people who have done, going back to astrophysical observations, shown that magnetic fields start playing a role. So would any of my friends in the audience have a better sense of when the earliest Dana, Mark, going back a long time ago. Right. Yeah, yeah. I can tell you how the Bierman works. I do know the mechanism, but yeah, that's the thing. Observational underpinning is a separate matter. But if you look at the people who measure magnetic fields out in the universe, Rainer Beck, Cronenberg, there are masters of this, that people have gone back and looked at this diagnostic, and they've dated their magnetic field, quasar intervenors and others. It goes way, way back. A question that always puzzled me was whether if you really had magnetic fields at the birth of the universe, would it have led to an isotropic expansion of the universe? Yeah, exactly. Yeah, and I believe that magnetic fields are not that important. There are bounds that people have placed on it. And this is part of the reason why I started, because you have people like you in the audience who are the astrophysics and not much plasma physics. But I think that people have put bounds on how large the magnetic fields can be. And what they find is that the kind of magnetic fields we are talking about were simply not probably present at the time. So it probably had negligible effect in the earliest few minutes of the universe. But thereafter, life becomes interesting. Okay. Thank you very much for your indulgence. I had to tell you about my students' result, because this is not a dead subject. It's very alive and kicking for me. Thank you all. A coffee break will be shorter. I apologize. Mark's lecture is at 10:30.